Hello everyone, it's our pleasure from Chris Phillips from the University of Oregon. So Chris is going to talk about the large finite values of Rokhlin dimension with commuting towers. Yes, Chris, please take the floor.
Okay, thank you. Yeah, so I should say two things before starting. One, this is joint with Elon Hirschberg. Yeah. The other is that I was actually choosing among a number of possible topics, things I will not talk about here, but if somebody wanted to hear some other time, might be possible. Radius of comparison of C of X. I'm actually giving a remote talk about that somewhere else on Wednesday. People want to join in, I think they surely can. I don't know yet through the Zoom information, but non-isomorphic simple AH algebras with the same radius of comparison Elliott invariant. That's not quite ready yet, but should be soon, I hope anyway. Incompressibility for Banach algebras, which is really not quite C-star algebras. Or the Treasure-Rokhlin property for actions of compact groups, including in particular examples. So those are all things which are sort of plausible to talk about. Okay, so I'm going to give the original definition of Rokhlin dimension. Commuting towers. I want to give this definition to make it look like the Rokhlin property, but I'm actually going to use a different one in terms of what we call the X-Rokhlin property, which I will reformulate afterwards. And that's what's going to be mainly used in the talk. And then in the rest of the first part, I will, once that's all sort of settled and this space is described, then I will say something about the construction of examples which give upper bounds, but the lower bound stuff requires equivariant K-theory, and that's what's in the second part of the talk. I should also mention, I forgot to write in my notes that, well, okay, I'll get to that in a moment. So generally, A is a unital C-star algebra. G is compact, usually finite or connectedly. A will usually be simple. Alpha is an action. And also Zn is C mod Nz, at least for today. Sometimes it's not. It might be the n-adic integers, for example. So I will say, let's see, let me put the word here at the definition. Alpha has Rokhlin dimension less than or equal to D if for all epsilon bigger than 0, for all F in A finite, there exists a family FGL of positive elements, norm FGL less than or equal to 1, for G in G and L equals 0, 1 up to D. So these, so if I fix L, I have towers. So this is a position in a Rokhlin tower. And these are the labels on the tower. Towers, sometimes called colors or something like that. Such that, so here we so FGL, FHL is 0 for G naught of H. So any particular tower, everything's orthogonal. It's 1, 2. Is that the sum over G and L of FGL at least is close to 1. So you essentially cover the whole space. 3 is that the norms of the commutators A less than epsilon for all G and L and for all A in this finite set F. 4 towers are approximately per meter by the group. Norm alpha H of FGL minus FHGL is less than epsilon for all GH and G, and L equals 0 up to D. And I just have room here for this one. And this is what's the difference between Rokhlin dimension with commuting towers. So with commuting towers, if also basically all these things commute with an epsilon, norm of FGK commutator FHL is less than epsilon for all GH and K and L. These were originally introduced for the purpose of trying to prove regularity properties of cross products and similar stuff. Some of the results needed the commuting tower condition, some not. And these conditions really are different, although I'm not going to say so much about that now. So this for G is finite. I should have said that. Here, there's a version for compact groups, which I will not put down. But I will put up next. We'll say that dim C rho of alpha is the least D for which the above can be done. So this is including 5. The superscript C is supposed to indicate commuting. If you leave it out, it's the other one. If D equals 0, in either case, you get the Rokhlin property. The point being that, okay, there's only one of these things. And so you have orthogonal elements which add up to something close to 1 and are less or equal to 1 and positive. They have to be close to projections. Functional calculus give you projections and won't fiddle either that or that too much. And they already commute. And so I should put example. This is for non-simple algebra. I'm going to let Z3 acts on C of S1, circle by rotation. I'll draw a picture of it. So this is S1. We'll identify the endpoints. And here is now one tower. So this one, for example, is F 0, 0, F1, 0. If I label the group elements as 0, 1, 2, F2, 0. And then the other one is this So this one, for example, this is F 0, 1. This is F 1, 1. And these two things together are F2, 1. So you have the towers allowed to overlap with each other. That, we're not assuming the towers are orthogonal to each other. Okay, so that's the setup I want to, or that's sort of the initial way things were defined. But I want to reformulate that in terms of the X Rokhlin property. So X is a compact. Well, and here will be, let's say, free metrizable space. There's no real need for it to be metrizable if you replace sequences with nets and so on. And for the purposes of just making the definitions, you don't need to be free either. But nobody's yet found any use for the cases when it's not.
What do you mean the space is free?
Metrizable G space, sorry.
Oh, okay, thank you.
Yes, thanks. Yes, there actually is a notion of a free topological space of some sort, but that's not what I want. And so now I'm going to say that alpha has the X Rokhlin property if informally. So there are, how do I want to put it? There are unital, sorry, I want to put, so unital completely positive maps. P C of X to A, which are equivariant approximately central and approximate homomorphisms. One would probably want to put approximate equivariant, but since G is compact, you can average to make them exactly equivariant without messing up the other properties very much. So we'll assume that. And so one can write a formal definition in terms of sequences. Well, okay, sequences, when X is metrizable, G is metrizable, and A is separable. But also also under those assumptions, so if A is separable and G is second countable, metrizable is not right, or maybe it is. Then it's the same as an equivariant unital homomorphism from C of X to the relative commutant of A inside this sequence algebra. So here A infinity is L infinity of NA mod C0 of NA, so the usual thing. Okay, if the group isn't discrete, then the action on that thing might not be continuous. But if you have an equivariant usual homomorphism, then the image always lands in the continuous part. So then this example, so if you look at this example here, so if you look at the three example above, then one more or less sees, I mean, I won't write down the details, that if alpha has the S1 Rokhlin property, then Rokhlin dimension with commuting towers is less than or equal to 1. Right, there's two of these things, but that corresponds to Rokhlin dimension 1. So more generally, take the universal C-star algebra, unital C-star algebra on generators FGL as above. And the relations are going to be, let's see, which ones do I want? I want this one, and this one hold, and this one hold exactly. Which are they? 1, 2, 4, 5. This should have been labeled. Lost the number. Such that 1, 2, 4, 5 hold exactly. Well, that's a commutative unital C-star algebra. Right, as C of X, G comma D for some compact G space X, G, D. So then what one gets is, so then one gets Rokhlin dimension alpha less than or equal to D, if and only if A has the XGD Rokhlin property. Actually, it's sort of a somewhat annoying thing, because at the time that, roughly around the time that Rokhlin dimension was devised, this is Hirschberg, Winter, Zacharias. So somebody told me at the time, or later, that the original motivation being the hope that one might find actions with this property on the Jiangsu algebra or on O infinity, where there are no Rokhlin actions. And about the same time, I came up with the idea of the X-Rokhlin property with the same sort of purpose, to try to find actions with this property on the Jiangsu algebra. And I spent a couple of hours trying to manufacture one with G is Z mod 2Z, and things weren't working very well. And so I decided, well, okay, I wonder what's happening. And I turned around and proved that no such action exists. Well, having discovered that no such action exists, I decided, well, this isn't maybe something to worry about, and I just gave up on it. And the whole thing took less than a day. Okay, so let's see. All right, I actually skipped one thing here. Yeah, I do want to, yeah, so I missed one thing which I want to say here. So I should have mentioned before. So one can show that given X, there exists a D, and this, of course, depends on G and X. And the action such that X Rokhlin property implies that the Rokhlin dimension with commuting towers of alpha is less than or equal to D. You can bound it by the covering dimension of X mod G. Oh, and I should say here, I want G to be a Lie group here. I'm not quite sure what happens if you don't have that. But the point is here that X mod G is a locally trivial principal bundle. Sorry, X is a locally trivial principal bundle with fiber G over X mod G. And the local triviality part is not true in general if G is not a Lie group. It doesn't have to be connected. It's bounded by this, but the D is finite even if the dimension of X mod G is infinite. All you need to do is to find some finite open cover which trivializes the bundle. But then there's this X GD here is sort of the universal space for that particular thing. And these things are finite dimensional. Okay. Okay, so this is not ours. This particular thing here is the place we found it written as a paper of Szabo. But then the question is, okay, what do these spaces look like? Sorry, that's not the thing I want to attribute. That's more or less immediate. This is the thing I want to attribute to Szabo. So what I want to know this, well, we're going to construct examples as the direct limit of things like the form C of X GD of various over n matrices, let's say R of n by R of n matrices with suitable actions and connecting homomorphisms. So we want to know what the spaces are. So here's how you construct them. So definition. Well, let me put the informal definition first. So for the moment, X and Y are just topological spaces. And the join, written with a star, is so you put together for all points, all pairs of points X in X and Y in Y, you connect them with a straight line. Line segment, a copy of 0, 1. So the only ones I can draw are when X and Y are finite, so that's what I'm going to do. So here's an example. X has 2 points, and Y has 3 points. And so I connect those 2 points, those 2 points, those 2 points, and also that, this, and this. So this is now a one-dimensional space, even the original things were zero-dimensional. And I should put, so sort of a remark which is not directly relevant here, but because you've actually, at least implicitly, probably seen such things before. If A and B are unital, probably even if not, then the tracial state space of A, direct sum B, is the join of the tracial state space of A and the tracial state space of B. There's, of course, more structure here. There's convex structure. So it's not something completely abnormal. So here's the formal definition, except that the formal definition is sort of backwards in the way I wrote the picture. So formal definition. I think the order I'm writing is standard, but in any case, it's X cross Y cross 0, 1. Well, it's an equivalence relation with X1, Y0 equivalent to X2, y0 for all x1, x2 in x and y in y. So this is on the right-hand side of the picture. But I take the lines from x1 to y and x2 to y, and they're just some disjoint things, but I want them to actually both end at y. And similar at the other end, x, y1, 1 equivalent to x, y2, 1 for all x in x and y1, y2 in 1. Okay, so here is one more thing that I can draw. So this is x is z2. And this is y is also z2. And what have I got to put in it? Let's find another color. Maybe that one will work. And here you see that x join y is homeomorphic to the circle. Okay, and so then the proposition, or sorry, I missed one more thing. So if x and y are G spaces, so is join. I use acting the obvious way. This action on this is trivial. On this factor, this piece is trivial. And the proposition, Savo, is that xgd is homeomorphic to the join of d plus 1 copies of G. So when d is equal to 0, I want to get 1 copy of G because the Rokhlin property corresponds to being approximately being approximately central, approximate homomorphism from C of G into the space X, so C star algebra A. And so this is shorthand notation for this. And there are D plus 1 of them. By the way, it's easy to get things off by 1, which we did several times while actually writing the paper. Questions?
But for t equals 0, right? So when you have the Rokhlin property, more or less.
Yeah, so I get the join. I just get one. I have one of those things. Yes.
Sorry. What is y? Is x and y
Are G spaces, arbitrary G spaces.
what is y?
Anything. Also any other G space.
The proposition doesn't.
No, the proposition doesn't have anything. Yeah, no, yeah. Sorry, but here I have an action. Is by translation on all copies of G. So in other words, I need this statement in order to make sense out of this. Okay, so I want to say a little bit more about these things. Also, maybe elicit some howls of outrage. There's a side comment which is going to be important in the second part. Let's see. I guess I can dispense with that. if X is a G space, you get a equivariant map from X to X, not convolution as I've tried to read this, X joined with G, which sends point little x to the equivalence class, I write it like this, of x1, 1. And so a couple of points of caution here. First of all, this is the identity element of the group, and this is 1 in the interval 0, 1. It doesn't look very equivariant. Since it is equivariant, since xg1 is equal to x1, 1. Right, that's the equivalence relation up, where is it? Up there somewhere. Hopefully you can get the endpoint switched. Right, so I was act with G on both of these things. So I should say Gx, G1 is the same as Gx1, 1. And then one gets the limit, the direct limit over n of G n copies n fold join. And this is the Milner model for the universal free G space EG. And then, of course, the direct limit of G mod G is for classifying space BG. There was one time when I was way back when I was a postdoc, and I had talked about something in the analysis seminar at UCLA, maybe it was functional analysis seminar, which used, it was actually about the Gettiga-Siegel completion for equivariant K-theory of C-star algebras. And then this thing had been used, and people wanted to know more about it. And so I gave some separate talk about classifying spaces of groups. And when I described this construction, Ed Erfros said, those topologists will do anything. Okay, let me leave that part. So there are things that I can't draw. Z2, D plus one of them, turns out to be equivariantly homeomorphic to S, should be D, just the D sphere, with the action X mapping to minus X. So the quotient is RPD. Well, okay, I've got the first case there. Maybe I can try to draw the second one. So here is that one. This is Z2 join Z2. And then here's another copy of Z2. Okay, so now I'm going to have a third copy of Z2, which sticks out of the board. One point out, the other back. And so now you can actually fill all these things in. So this is the top part of an octahedron. And a different color. The red is the bottom part. Well, maybe I should say front and back part of an octahedron. And so I guess you can sort of see how this goes. And the other one, for which is a nice description, is take the circle group. This turns out to be the 2D plus 1 sphere. And the group action is scalar multiplication from S2D plus 1 as the unit sphere in CD plus 1. I cannot visualize it myself. This is what actually happens. Doesn't even, people just seem to, topologists just assert this without actually writing down a proof. I'm sorry to say.
What do you mean even for small d?
Yeah, I don't even see it. Yeah, well, I haven't really tried for d equals 0. Sorry, for d equals 1. For d equals 0, of course, it's all.
All right.
This might give you a misleading impression of what these spaces are like. Go back to this one. See, this one is one-dimensional, but not a manifold. And if I took Z3 and Z3, I would get 6 non-manifold points. And things will get worse. It's a finite complex. But what they look like, and topologists have paid little attention to them as far as I can tell. So I should say what one can say about these things. Okay, I wrote Z3, join Z3 in my notes, but anyway. Okay. Some things can go nicely. And this is going to be wanted later. You can compute the K-theory of X join Y from K star of X and K star of Y using Meyer-Via torus. E or A, I can never remember. E, okay. And cadet formula. And I'll just draw a picture, again, with finite X and Y. So since I'm doing K3 with compact supports, I'm going to use closed sets, but this will be U up to here. This will be V. Cut them off like this. And then one gets U is homotopy equivalent to X. This is X here. V is homotopy equivalent to Y. And U intersect V is homotopy equivalent to X cross Y. So you can iteratively compute what the K-theory of multiple joins is. And in particular, you can check the following. If you take the join of, and now I'm going to get parity off unless I actually check my notes, of d plus 1 finite spaces, and d is odd, then you find that K0 join, call it Z, of Z is finitely generated torsion free, is torsion, is, let's say, finitely generated free abelian, and K1 of Z is 0. Did I do this right? If D is, no, D is even. Right, if D plus 1, I want D plus 1 to be odd, because it's where, yeah, D is even.
So what happens with the other?
They're still both finitely generated torsion free. You end up with, I mean, I wrote down in my notes the actual formulas you get in terms of number of points. But you get K0 is just Z and K1 is a big direct sum of copies of Z. So there's a piece which stays entirely always in the K0 part, which just comes from the fact you have a connected, okay, except for 0, D equals 0 compact space. And then the other stuff flips back and forth between the K1 and K0 every time you add a new join factor.
That's sort of thought period.
Yeah, probably. You need a byte periodicity to prove the Meyer-Vitor sequence in usual ways. Okay. Okay, so now I want to tell you how to construct an example. Yeah. An example. Of an action. And in the example, let's take Z as Z3. Maybe I should have taken Z2, but this one is at least maybe a bit more realistic. But it gives me the opportunity to get some unitary matrix backwards. But the idea works for any G, for any finite G. So I'm going to take X is going to be X, Z3, and D. So D is fixed. I get something with Rokhlin dimension less or equal to D. I will take AN is C of X M4 to the N with the action by on C of X from that on X, and some interaction on the matrices. It will turn out to be conjugation by the tensor product of so and so many copies of the direct sum of the regular representation and the trivial one-dimensional representation. But I'm not going to write down all that things down all that far. I'm just going to write down enough so you can see how one should actually go about doing this. And so I want to get a simple direct limit Oh, and I want to take here, and I want to take D should be even. Won't matter for a while, but eventually I'm going to want that. So I'm going to tell you, so first I'll tell you what the map is. So A0, this is C of X to A1. It's going to send F to some 4x4 matrix. It's going to be diagonal matrix F. And now I want to put a point evaluation in here because I want something simple in the end. Putting only one of them, I'll get in trouble. But I do need points, so I will take x1, x2, etc. in X dense sequence. Should say all tails dense, but that's automatic because the space is connected. And now, oh yes, and I also want to give a name to the generator. Let H in G be a generator. And so now I'm going to put here F of X. Let me just take, no, I don't want to use that. Let me just take, looks ugly in my notes. Let me just take Y equals X1. So as to avoid confusion with various X's and so on. And also subscripts, that's the real issue. F of Y times the identity times the constant function 1. Here's a point evaluation. Leave enough room there. F of H applied to Y. And F applied to H squared applied to Y. Okay, it's a perfectly good homomorphism. It's got 3-point evaluations instead of the one that you might have expected. Any questions?
So your action on the A just the check the action just by action X.
And some interaction on M4 to the n. And I'm now, the next thing I'm going to tell you is what that action is going to be for n equals 1. Because you see, if I just take the action on X induced by the group action, or on C of X induced by the group action, and I put something like this, there's no way I can make it equivariant. So I'm going to choose an action which does make this equivariant. Yeah. So to be explicit, alpha 0 H of F at X is just F of H inverse X, what you would expect. This is on C of X. And on C of X, M4, alpha 1 of some function F at X is going to be, well, I'll do this. Now I'm going to take some unitary. So this is M4 tensored with C of X. And then, well, let me just put V here. Star, tensor 1. And V will be U1 in a sequence U1, U2, etc., with UN in the unitary group of the 4 to the n by 4 to the n matrices. And what's V going to be? 1, 0, 1, 0, 0, 0, 1, 1, 0, 0. Okay, so I actually So let's just see how this fits. Let me call this thing, this is phi1 of f, let's say. So just to compare, phi1 of alpha upper 0 h of f is going to be. So now I'm going to take f of h inverse x. I'm supposed to put that thing in there. And then here I have to put f of h inverse, or rather I have to take the f of h inverse part in here and do this. I get f of h inverse y. That's a constant, right? Because this is for x in x. Remember, y is x1 in x1, x2, etc. And then I have f of y. That's applying the f composed with h inverse. And then I have to take h of that. And then I get f of h of y, h applied to y. 0 is also. Okay, if I did things right, then this is the one which conjugates this thing to the thing I had over there. There's only one other possibility, which is to replace v with v star. And so I want to point out that so there is a representation of G involved here. It's the direct sum, the one-dimensional trivial representation. Direct sum, the regular representation. Okay, so then you have to proceed inductively and defining U n inductively. What you'll end up with is a tensor product of so and so many copies of that. If I remember correctly. We did not write it down just to find these things inductively. And if the group is not at least cyclic, then the notation for this gets rather ugly. Yes, I'm supposed to have an intermission in a couple of minutes, right?
Technically, that's supposed to be 4 minutes ago, but.
Oh, sorry.
but-
Okay, I misinterpreted the time.
We need to finish the idea.
Yeah. Sorry, I thought I was supposed to stop at 3. And so you construct an, Pn, an minus 1 to an inductively. And it turns out that classification that A equals direct limit an is a simple AF algebra with a unique tracial state. And the XZ3D Rokhlin property. So the Rokhlin dimension is less than or equal to D.
You get it, say, by classification.
That's right. That's why I wanted this D to be even, so that K0 of that space is 0. So the space that I used here, when D is even, K0, this thing is 0.
Is zero? No.
Is sorry, K1. Sorry, K1 is 0.
Okay, that's what.
Yes, K1 is 0. So after the break, I guess there's 15 minutes or something, I'll try to tell you how to show that the Rokhlin dimension is not 0 or 1, at least if D is large enough. And in fact, we made arbitrarily large.
Okay, let's resume our second part of or second talk with Chris Phillips. So Chris, please take the floor. The same topic, I think.
Well, I should have given it a different title. I should have given the title Equivariant K-theory. Because at least initially, it's not going to seem to have anything to do with what I did in the first part. But the connection will come later. So I'm only going to talk about K0 and for unital algebras. So G is compact, A is unital, alpha G to aught of A. Let me start with the case when G is not present. Since A is unital, K0, well, let me start not with K0 of A. Let me start with V of A. Is a set of Murray-Bannerman equivalence classes of projections in M infinity of A, which is the union over N and N of A. I could take K tensor A here. Doesn't really matter. I don't get any new equivalence classes. I'm going to implicitly, so I'm not going to say anything about details. I'm going to go back and forth between this and I guess it's called algebraic Murray-Bannerman equivalence. So the appropriate version between this and idempotence with the appropriate version of Murray-Bannerman equivalence. This is something I really want to sweep under the rug, but I can't completely ignore. And what is this? E is equivalent to F if there exists V and W such that WV equals E and VW equals F. An idempotent just means that E squared is E without assuming itself a joint.
I suppose I call this
Yeah, the places I've seen called algebraic Murray-Bannerman equivalence, or sometimes just Murray-Bannerman equivalence.
The plans to be did it very systematically in the early 50s. And then it's not known if it's equivalent to the star version, except in the C-star, being taken on for star algebra makes sense. The question makes sense.
Yeah, I think it's still open. I assumed it was false.
Yeah, well, sure, okay.
But I admit I did not know any actual counterexamples, but I can't believe that in a general Banach star algebra that they're the same. Well, for that matter, yeah, if you use the star version in a Banach star algebra, I can't believe you even get the same group all the time. But I certainly don't know any examples. Well, I also don't know. I mean, surely it's false that the direct limit of simple Banach algebras is simple.
Okay, yeah.
Right, it's true for C-star algebras, but that uses special properties of C-star algebras. On the other hand, I've never actually seen a counterexample
Maybe you don't want to see.
Well, okay, there is one vaguely related horrible example with a Banach algebra, which is purely infinite, but not uniformly purely infinite. If I ever talk about incompressibility, maybe I'll mention it. Anyway, so then K0 of A is the Grothendieck group of V of A.
This group was not invented by Rokhlin. It was invented by Russians 10 or 20 years earlier.
Uh-huh.
Not to mention people in grade 2 going from natural numbers to anything.
Yes, so this reminds me the Tikhonov's theorem was proved by Čech, and the Čech or stone-Čech compactification was invented by Tikhonov.
But the trouble with calling it the Grothendieck group is it makes people think that that's what Grothendieck is. I mean, but he just used K0 for amazing things.
Yeah, so no, there's this enormous amount of algebraic geometry stuff that is somehow foundations of the subject these days. But that's right. So now I'm going to so let P in let me take an idempotent here in Mn of A. So I'm going to say this acts on A to the n by, let's say, left multiplication. And Mn of A is the morphisms of A to the n as a right A module. And so we get EAN, which is a right A module. And it's finally generated projective. And for the purposes of this talk, you may just as well assume that means it's a sum n in a finally generated free module. E and n direct sum 1 minus E a n is isomorphic to a n. And then Murray-Bonhomme equivalence corresponds to isomorphism of these modules. Right, the V is the isomorphism going one way, and W is the isomorphism going the other way.
To show that you just look at left modules or right modules independently, then you get the same group.
Yes. It doesn't matter. I have to make a choice of side, and then the one I chose is what's commonly done. But it's exactly the same if you do it the other way around, except you better not mix them.
But the funny thing is, if more general classes of modules, you still get a semi-group. That is defined the same way if you get a group. And it's not clear that left and right will be the same thing.
Yeah, there are lots of things where left and right don't obviously give you the same thing, but it turns out they actually do, or where they don't give you the same thing at all. For Banach algebras, left and right stable rank are not the same. Well, the K0 has to be, but the other ones, I don't know. Yeah. Okay, so I'm going to reformulate V of A is the set, only now I have to be careful, and I'm going to suppress the technicalities of isomorphism classes of finitely generated projective write A modules. And I'm going to suppress the word right everywhere from now on.
Why is it set? Because just take the free module, L0 free module, so everything is quotient.
Yeah, well, that's how you make sense out of it as a set. But the problem is that that any particular isomorphism class, if you take all possible modules isomorphic to that one, that's not a set.
So, okay.
But yes, there's easy fixes by just
You go by the principle that you have a set, then the elements of the set have to be sets.
well, I think that's among the axioms of ZFC. So,
Then you can't say an isomorphic class is just a single set.
no, it contains all the modules isomorphic to that one. Okay, so now put back G. A module E. Well, I should really say with an action epsilon. From, let's say, G to just the linear operators on E is equivariant. And this is the only kind I'm going to talk about. If so, these are not module automorphisms. Epsilon G of Xi times A is equal to epsilon G of Xi times alpha G of A for all Xi in E and A in A and G in G. If I put module automorphisms, I would have A there instead of alpha G of A.
Okay.
A is this C-star algebra.
Oh,
A-
Action of G on A. Right?
Yes. So okay, this is the, yeah, G maps to epsilon G, which is an epsilon G is a linear map from E to E. Linear and continuous and so on. Okay, I could have avoided the idempotence by assuming scalar products on all my modules and so on. I don't want to carry that machinery around. That's worse, I think, than what I did. So, and then take VG of A. I should really put an alpha in here somewhere, but I will omit it, to be the set of isomorphism classes of such E for which the underlying just A module is finitely generated projective. So we decide on finite generated projective without paying any attention to what the action of E of G is. And the operation is direct sum. And K0 G of A is the Gordon D group. Or if you want to call it the 20 years previously Russian group. Not quite sure how to make a short formulation of that. Oops. Sorry? Yeah, you got to be careful if the thing isn't abelian. And sometimes you get disasters, but I don't remember details. Okay, so this is for A unital. You extend to non-unital A, unital A, and to K1 G of A in the usual way, as the same as if without the group, and in SA, G in the suspension, D does not act in the suspension direction. You can actually say something if it does, but that's not going to be relevant here. So it's a theorem, which in the paper of Schulk, but apparently also of Green, which is that K star G of A is isomorphic to just the ordinary K theory of the cross product. And you may wonder why I didn't define it that way, but you will see. Okay, let's look at the special case. A is the complex numbers. There's only one possible action. dg of C is the isomorphism classes of finite dimensional representations. Of G, or in here we can easily go back to the unitary case, unitary equivalence classes, finite dimensional unitary representations. And then K0 G of C is the corresponding group. The group formal differences. Yes, sometimes it gets used. So tensor product of representations is defined and makes this thing a semi-ring, or whatever the right term is. And in particular, K0G of C, a commutative ring it's got a special name, R of G, the representation ring of G. And I should have put this in my notes and forgot to, but I'll say it anyway. If G is abelian, R of G is the integer group ring of G hat. Or G is compact, so this is some discrete abelian group. Moreover, you can form E tensor V. This is, maybe I should say V tensor E. V finite dimensional representation. E equivariant module for A. Then V tensor E is an equivariant module over A. And this makes, well, K0, but in fact, K star G of A, an R of G module. Since R of G is commutative, I don't need to worry about the difference between left and right. And this is what you don't see in this theorem. Although once you know that structure is there, you can in fact recover it. So if G is abelian, then the action of something in G hat is just the dual action here. But it gets more annoying to write down if the group is not abelian. And two more things. R of G has a special ideal. I of G, which is the kernel of the map induced by taking a representation to its dimension. So it's all the things at virtual dimension 0. It's fairly large. The quotient is just the integers. But it's not maximal because integers are not field. And the other thing I should say is that K star G of C of X is the same as the equivariant K theories defined for spaces star G of X. And it is a ring. And I'll only use the K0 part. Well, in the way things set things up, if A is abelian, then right and left modules are the same. And so you can take the tensor product of two right modules and get a module. If it's not abelian, the best you can do is take the tensor product of a right module and a left module, and that's not a module on either side. Or you can think of getting it in terms of vector bundles. Okay, so that goes to here. So now here are sort of the key results. That's very good.
You're not going to give me a photograph?
Sorry of that.
Well, I mean,
It's in the recording.
slide plot.
No way to show it here. I have some. I'll use one in the radius of comparison of C of X talk next week. But yes, I have no convenient way to display it here. So. Yes, so key facts. And these are old or else sort of reasonably clear. This one is old. And it says I of G to the D. And let me get don't want to get this off by 1. Times K star, yeah, star goes up there. G of the D fold join is 0. Two, for all G, for all D, there exists an N such that for all K bigger than or equal to N, I of G to the D, K star G of the K fold join is not 0. G should not be trivial. For D, yes, yes. Yeah, if you take, let me say, just to be safe, D is bigger than or equal to 1. But I of G to the 0 should be the whole ring. Yeah, so it should work there because I of G to the 0 should be the whole ring. And G star 0 is a point. And so it would claim R of G times R of G is 0. Well, okay, that's not right. Okay. And so now I want to relate to here I'll make the comment. I won't actually write it down because I may run out of time, but this statement is true for the spaces Xn, let's say, in any realization of EG as a direct limit of finite complexes. So there's nothing special about these things. And this is where somebody brought up the issue about homotopy choices and so on. This is the sense in which it's insensitive to that sort of thing. But on the other hand, if you change the spaces, then this one happens to actually come out exactly right, and otherwise will not. The other thing is that for most cases of groups, one doesn't know how to get K from D. And the topologists seem never to have looked at it. I'll mention the cases I know. So here is the third thing. Suppose A has the X Rokhlin property and I of G, let's say to the n, K0G of X equals 0, then I of G to the n, K star, no, let's go over here now, star G of A is 0. So, I'm sorry? Suppose, yeah, A is a C star algebra with an action of G. Unital should be alpha G to R of A. And X is some G space, is a compact great G space. This is an X. Okay, so I'm going to get lower bound. So I'm going to prove that I of G to the n times K star G of A is not 0 for suitable choices of n, G, and A. So why is this the case? Well, if you have C of X to A unital equivariant homomorphism, then K star, no, it goes down here, G of A is a K0 G of X module. Remember, this is the same as K0 G of C of X. Okay, so you just run this through the module operation. For the X Rokhlin property, this is not quite true, but it's close enough that you still get this statement. You'll actually still get a module structure if you have the continuous X Rokhlin property. But if you just have the ordinarily defined one, then you don't quite get that. But you get good enough for that statement to be true. Okay, so I'm going to leave that thing. So if we combine 1 and 3, and I want to get this off by 1, so let's actually write it down. If I of G to the n, K star G of A is not 0, then the Rokhlin dimension alpha is bigger than or equal to n. And the danger, I was off by 1. Notice that I've got a d and not d plus 1 there. Okay, so now I want to tell you how to show that this one has what this is part of the example from the end of last time, has large but Rokhlin dimension. So consider C3 example above. Fix n. Choose d even with I of g to the n, k star g of g p plus 1 full join, not 0. Okay, so let's recall. This is more or less looks like that. Phi of f is f, and then f of this is just c of x to c of x m4. F of y, f of hy, f of h squared y times the constant function 1. And so you see, I mean, the equivariant K theory doesn't change when I tensor with the conjugation by some unitary representation. You have to check that. But now let's look at what the map does. Oh yes, in the map, the action does, it was right, it was alpha 1 h of f is it should be at x was equal to v tensor 1 f of h inverse x v tensor 1 star, and v is, well, I'm only taking one generator there, but it is this one-dimensional trivial representation, direct sum regular representation. So this is say 1 plus rho. So on equivariant K theory, P is multiplication by 1 plus rho in the representation ring. And this is true at all the levels. Now I'm going to multiply this by the augmentation ideal. So now I get multiplication by, well, it's really still multiplication by 1 or whatever, plus, well, okay, I'm going to cheat slightly here. So multiplication by 1 plus whatever the augmentation ideal does here. The point is that by rho, say rho times I of g to the n times whatever This is 0. Why is that? Well, rho is the regular representation, and the regular representation, since there's any other representation, is just direct sum of copies of the regular representation. This is what I learned recently. This is called the Fell absorption principle. So anything in here is the formal difference of two representations of the same size. Multiply that by the regular representation, they become the same. Therefore, on I of g to the n, k star g, I have multiplication by 1 at all stages. And so what's the conclusion? Thus, I of g to the n times k star g of a is not 0. Therefore, dim c alpha. Sorry, I want to put here n is less than or equal to dim c alpha less than or equal to d. N was arbitrarily large and d is finite, no matter what n is. Okay, so let me just say a couple of things and raise some questions. So if G is Z2, the dependence of D on N is known. It's part of the method that this, I guess, most common method that's used in textbooks to compute the K-theory of real projective spaces, which is to say it's the equivariant K-theory of the Z mod 2Z action in the sphere. And one gets alpha on a simple usual AF algebra such that n less than or equal to dimension C Rho alpha less than or equal to 2n plus 2. That's the best these methods give you. Question: what is the true value? If you take C of x, well, specifically if you take C of the appropriate join, then you'll find out that the Rokhlin dimension of the action on the universal space for Rokhlin dimension D is in fact exactly D. You would certainly hope that would be the case. This is true. It's basically been done by topologists. But the methods are things which, as far as I know, have no plausible generalization to C-star algebras. And my suspicion is, if I had to guess, I would say the answer is n. This is a somehow suggested by the results of the Elliott classification program, that K-theory should tell you everything about this sort of thing. And finally, one more thing I will state, and then one comment. if G is the circle, well, then point evaluations don't work. But the complicated method we used has a cheap alternative. And one gets for all n, there exists a classifiable unital simple. It should actually be a T algebra. I guess I don't need to classifiable automatic in this case. A and alpha G to R of A, such that Rokhlin dimension of commuting towers equals n. And again, this comes from known equivariant K-theory computations. These are related to the computation of the, although this is, I think, not normally how it's done, but the K-theory of complex projective spaces. Yes, because you see what happens is when you to get not annihilated by, see, when you increase n, the thing gets smaller. And so in the real case, you want to go up by one more power of the augmentation. You have to increase the dimension by 2.
Yeah.
And there you have only increased the dimension by 1.
Well, the real dimension still.
Yes, well, okay, but
Well, yeah, those types.
but you increase the number of join factors by 1, and here you have to increase the number of join factors by 2. Another question for some topological minded person is, okay, how do these things, I guess it's gone now. In the more general case, how do these things actually depend on the number of join factors? Nobody's paying any attention to that, as far as I know. It's probably known for, and never thought of doing this, for quaternionic projective spaces. Okay, so I will stop here.